now my great pleasure to introduce Animesh. Animesh is a research scientist at NVIDIA and also an assistant professor of computer science at the University of Toronto, as well as at the Vector Institute. He earned his PhD from UC Berkeley, where he worked with Ken Goldberg and Pierre Biel. And his group aims to build algorithmic foundations for generalizable autonomy that enables robots to acquire skills at both cognitive and dexterous level. And what's very important, and I think interesting also, why we think he's a very good fit to this workshop, that his research interests are in one of his many research interests is in introducing structured inductive biases in deep learning. And we also believe that implicit representations is one way of achieving this. So we are looking forward to your talk now.
Thank you very much. This workshop has been wonderfully organized with a very thoughtful set of speakers, and I've had a lot of fun through the day, to a point where I'm actually feeling bad for not being there in person. But thanks a lot. And by the way, Judgin, this was a wonderful talk, and I would love to be able to follow up. So in the interest of this idea of using implicit representations for robot learning, I thought that instead of just providing you with an overview of stuff that is public, I'll hope to fashion this talk a bit more around stuff that is in the works that hopefully can lead to more discussion. So with that, we've already seen, I think, a number of interesting talks that already talked about this idea. I think the core interest in implicit representations is because a lot of the current representations that we use have a variety of advantages, but many disadvantages. So if we look at just the representations for visual computing, let's say 3D data, a lot of them are discrete, whether you're using voxels, point clouds, or meshes. While this is very intuitive mechanism of specifying data, they have problems in memory. If you are using point clouds or meshes, then connectivity structures are lost, or meshes don't always have ability to capture arbitrary topologies. And this is where this idea of implicit function representations has been very powerful, because in principle, they promise to solve a number of these problems of either continuous representations, infinite spatial resolutions, and often representation complexity depends on the signal complexity. So if you're interested in capturing a sphere like an apple versus, let's say, a complex shape like a bench, then the object representation complexity drives how complex would the representation be, not necessarily the choice of representation per se. And of course, now you can think about what are these functions. Essentially, these are functions that are mapping in a continuous spatial space. If you think about an image, you're basically creating a function where you can query X, Y, Z, and it will output some RGB. And now you want to capture that in an analytical form. And often, for practical use cases, either in vision or robotics, this analytic description would not be tractable. And that is where implicit neural representations come in. So essentially, we are interested in these functions that map from coordinates to values. In cases of images, they can be XY coordinates, outputs can be RGB. As we've already seen in nerves, that these can be XYZ and viewing angles, and then the RGB and sigmas. And then we can also use a similar function to capture not just visual representation problems, but also spatiotemporal representation problems, such as trajectories. Trajectories can be of generalized coordinates, and then the output can indeed be, let's say, some utility function, whether scalar or vector function. And of course, we've seen a number of interesting works by a number of authors, too many to even review. The TLDR would be TLDR here, where we have used implicit representations for problems in shape reconstruction, rendering, view synthesis. We've also seen a lot of interesting work in the space of robotics, where people have used it for detection. The organizers themselves have used it for visuometric control, and some very interesting work in object representations, which allow you to do generalized manipulation. So what I thought was, I would go over some of the ongoing works in progress for problems that we believe using implicit representations are incrementally important. So I thought I'll give you 3 particular snapshots. One is in perception. How can we do better pose estimation and registration when object models are nerves? Next, we'll talk about how we can use implicit representations for modeling trajectories. And finally, we'll talk about how these representations actually help us do better simulation, which in turn allow us to do better planning. So let's get started. The first problem I want to present is work led by one of our PhD students, Lily Goldie, in collaboration with Dan and Andrea. And the key problem that we are interested in is now we are going to have a lot of data sets that are essentially nerve models of objects, right? So, for example, what Jiajin just presented, you can have essentially libraries of nerves instead of meshes. Now, what happens with this? Well, nerves are trained with particular scenes in particular lighting conditions when camera moves around in a particular manner. But often what will happen is you'll probably have nerves that are either of partial views, so you don't always get complete 3D models, or you get these 2 objects that are the same object essentially, but captured in very different settings. Hence, the direct nerve matching would not work. Why? Because nerves do implicitly capture essentially radiance or RGB values, which depend on lighting and which are hard to sort of be generic across. However, in robotics, if you want to use nerves as object models, you still need to solve the problem of essentially object registration across scenes. So the problem is essentially you are given 2 nerves, let's say a memory object in your memory and an object that you encounter in the real world, and you have to register this. This is an age-old problem that people have solved in multi-view registration, point cloud registration, and a variety of settings. However, the problem when object is actually a nerve model, surprisingly is tricky. And of course, once you can do that, the interesting application it opens up is how do you do now for an interactive scene, you can now essentially align a model in that scene and then interact with it in a simulator. So I'm going to spare you the details of how nerves are set up. I'm assuming it has been done multiple times during the day. But the primary thing to understand here is that these models are essentially trained with RGB values and particular camera viewpoints, and that they output for a particular point in space, RGB and the radiance. So the problem now is very simple, actually. You have 2 objects or 2 scenes where you have 2 separate nerve models collected by, let's say, a different set of data collection process. These can be scenes with different lighting conditions, different backgrounds, and so on. Now, what we want is, given these 2 nerves and some correspondences, find the right corresponding transformation that will align the 2 scenes, which is a problem that we solve in 3D vision multiple times. So now you can really think about this as a problem which can be set up as a simple loss function. One is basically the differences between the rendered scene, and the other one is if you're given a few correspondences, they should match up. Nothing too complicated. But there are 2 challenges here. The problem is, even if you have learned this sort of transformation, the rendered images will not completely line up. Why? Because the scenes are only partially overlapping. And then correspondences only are in 2D, but transformation is in 3D. So solution to this is essentially we need a robust function to handle robust point cloud matching, in a sense, in 3D. And then we need to use equivalent 3D points that go from 2D correspondence points and then do registration in that space. So for the first term, which is basically a robust loss function, what we are interested in is to find, this is something that was initially proposed in CVPR by John Barron, but the idea is that if you want to do registration of 2D views, you have to model the problem in a simple 2D setting where you have a set of points and you want to register them. The question or the interesting argument that takeaway from here was that instead of modeling the whole scene, just focus on the objects of interest, and then many of them can be aligned point by point. Now, the question is, how do we get these points? So these saliency points can be recovered from a variety of different algorithms. And in this case, we use learned saliency points on the objects rather than the background. That allows us to define what object of interest are we trying to align to in a scene, because in general, nerves capture full scenes, not just objects, right? So now we have two nerves. What you see on the left and the right are basically two separate nerves that need to be registered across. And now we are doing essentially radiance matching for particular points. This is good, actually. This gets you very far. However, the problem is if you only use radiance for registration, we will essentially result in fails, particularly, for example, symmetry or when lighting condition changes. So that is where we can fix this by adding geometric features, 3D geometric features, rather than just pure radiance features. So when we are generating points that are salient on the object, we should not be just looking at texture on the surface, but actually geometric features. Now, how do we do that? Well, we trained a model in this case that learns to sample points on the boundary of the object. This allows you to get a refocused sample of points on object boundaries. And essentially, now with the combination of these two losses, one is in radiance and one is in geometry, you can get reasonably good, actually, nerve-to-nerve registration setup. So now what you see is basically two partial view nerves for a scene, and you optimize the registration. Registration process is basically an optimization process over point clouds. But the final overlay shows that the objects of interest directly can be registered, even though the scenes and the backgrounds may not always match up. So we can do object-oriented or object-centric scene representations where we can align two objects where both the representations for objects are implicit maps. So what I gave you is basically this glimpse into the work that we are doing for object representations. Now let's flip the question and see, what if we were to use the same idea of implicit neural representations, but this time around to capture trajectories in the scene? So this is work that one of our PhD students, Yunzhu, did in collaboration with Aditya Murli and Bala at NVIDIA. So what is the problem we are looking at? We are looking at essentially doing reactive grasping. So let's look at what current grasping models do. Currently, what would happen in a standard model would be, there would be a camera overlooking the object. You would look at the object of interest, you would detect a grasp pose. You would find some sort of inverse kinematic or inverse dynamic solution for the robot to go to this object pose in the camera. And then you'll plan a collision-free trajectory. And this last mile is often done in open loop. Of course, there are some use cases of people trying to do this in closed loop in top-down settings, but not necessarily always in 6DoF. So now this works when you're doing this sort of tabletop object grasping or even bin picking. But there are very many discrete grasp modes for every object. And what if these objects are also moving, or maybe you're interacting with an agent that is, let's say, a human who is doing handovers. Essentially, in those cases, this pipeline of static grasp, predict, and then reach would not work. In that case, we need to learn essentially a mechanism to do reactive grasping. So what we said was, what we can do is we can solve this last mile problem essentially by learning a value function. So what is the value function we are interested in? We are basically arguing that given an object point cloud or a scene point cloud in some setup and a gripper pose that we are interested in, we can predict the path length to a grasp. The path length can be interpreted as essentially a mechanism of value function. Essentially, think of this as path length is a good measure of the solution length or distance to go, and value functions implicitly are essentially measuring distance to go. So Smaller path lengths are always preferred in that sense. So we are interested in basically building this value function, which is implicitly capturing the scene and the grass pose and directly predicting the path length without explicitly doing the planning online always. So what we are going to do is we can basically set up the problem as a sequence of as a trajectory, and then we are essentially computing a cumulative or integrated path length here. How is this model trained? You can query gripper poses and create paths by using planners. In this case, we can use sampling-based motion planner with a rollout style framework to create data online. In this case, we used an algorithm called Storm, which is a GPU-based motion planner for these sort of robot motion generation problems. So that allows us to create a lot of data that allows us to train this implicit value function. Now, you can train this value function and we can ask this question: how much data do you need to train this thing? An interesting question, interesting observation we found was when we are evaluating this on only static objects, then a lot less data would do the trick, which would be very obvious or rather not surprising in a sense. About 5% of data gets you in the same ballpark in both rotation and translation error at the end. So this error here is the error of the pose at the end of the trajectory. And then when you have dynamic objects, so objects are moving around, in that case, what we notice, translation is fairly easy to learn. However, rotation is the thing that is harder, and getting into the right 6-dot pose requires a bit more data. And then we observe something similar as well, that the data itself needs to be diverse. Essentially, we are modeling a multimodal distribution. You are looking at an object and you're looking at different ways to grasp it. And your value function is essentially snapping to the closest grasp. So if your data has many more initial grasps, then learning is a bit more efficient. Let me show you a simple demo of what that means now. So essentially what you're seeing is a robot using this value function to, using the gradient of the value function to go to these poses. And now if the object is moved around, the robot reactively goes to the closest possible grasp. And notice that the robot will be aware of the collisions between itself and the object. And this is important because implicitly the data generating mechanism was a motion planner, which was doing this through collision aware trajectories. Hence, the robot does learn this in the right configurations. Okay. So far I talked about two things, which was that you can use this idea of implicit neural functions to either solve problems in perception and action. But a lot of the times we actually want to use better simulators. As one could argue that a lot of the robot learning problems are these days attempted, if not solved, in simulations. So this is a line of work that we've been pursuing for differentiable contact-rich grasp synthesis, led by Dylan Turpin, who's a PhD student at Toronto. So what is the problem? What we want to do essentially is we want to use SDF-based contact forces in the simulation, friendly for gradient-based optimization. In effect, we are trying to create a differentiable simulator where the underlying representations for objects are SDFs. Why is this interesting? Well, differentiable simulators are interesting because high-dimensional contact with scenarios are hard to learn explicitly from sampling-based methods. But there are problems. One is context sparsity. Often, most other simulators only result in very sparse contacts at any given time, and inactive contacts have no gradient. So creating a gradient-based method in this case becomes slightly tricky. So that's one problem. The other problem is the object representations are actually locally flat, right? So even though we are talking about representations of objects which are smooth, but underlying, if you're using meshes, they're based out of tetrahedrons or triangles, and triangles are locally flat. So if the triangles are locally flat, then surface normal gradient is going to be actually 0. So you cannot do really much because, well, there is no gradient to improve. And finally, object geometry is not always going to be simple convex shapes. You can have arbitrary shapes, and surface normals can often be discontinuous. So again, this can be tricky if you're using gradient-based optimization. So the solution for each of these problems is, for contact sparsity, we use leaky contact models for handling gradients. For handling objects, instead of using simple mesh objects, we use Phong SDFs, which I'll talk about how they work. And for non-smooth object geometries, we use SDF dilation. So the problem of interest is basically trying to generate multi-fingered contact-rich graphs that are very natural through gradient-based optimization, something like this. What you're seeing is basically an optimization process running directly without any priors on what the grasp should be. So the contact sparsity problem can be really thought of as that you're given a particular grasp pose, you run the simulator, you find the object sort of pose and grasp pose, and then you're given some sort of task loss. The task loss may be, let's say, grasp stability. And what we are interested in, because this is a gradient-based optimization, is basically the final task loss, stability of the grasp with respect to what the hand can do. Now, the problem is that this proper gradient is going to be non-zero if the object SDF at contact location is less than 0 and 0 otherwise. That can result in a problem because, in a sense, until the contact is made or a new contact is made, you have no gradient to follow. So simple gradient-based optimization methods would often stutter. So a solution to this problem can actually be done by adding essentially a leaky gradient. This is a trick that we use often in deep learning. In a sense, what we're doing is we're basically allowing the gradient when the contact is not active to be non-zero, which allows us to have some small gradient to enable new contact. So when the hand is not in contact, then it should still arrive to make contact. Now, the other problem, as I mentioned, was this idea of local flatness, that even in simple object geometries, let's say constructive solid geometries, the representation or the underlying representation is a flat mesh representation. And that can result in incorrect gradient computation. So a solution for this is what is called Phong tessellation, a trick in graphics, which is used for shading objects with underlying flat meshes. In a sense, what is done is this is local averaging of the gradient vectors to enable smooth transition across spaces. Now, even with all of this, essentially, you're not going to optimize over a spherical representation of a cow. That's easy, but most cows are not smooth. So then what happens with discontinuities in surface normals? Well, it results in discontinuity in contact normal, and as a result, optimization becomes trickier. And this is where we use SDFs and their property of smoothness throughout. So we argue that SDFs are easy to smooth because you can really think of it like this, that SDFs at level set S are level set of the surface is 0. But if you allow certain smoothness for adding, let's say, padding to the object in a sense, then you can adaptively change the SDF slightly such that initially you start with a gradient of the object that allows you to arrive at the object geometry for simple shapes. And then you can adaptively change R such that as optimization progresses, you're actually optimizing for the correct object shape. And then you can do the same thing for robot grasping, where hand reshapes as if grasping a larger version of the same object. That's the same idea. And the same trick would also work in general if you have concave corners. So now, simple concave corners won't work. And in this case, what we do is you have to adaptively change the SDF model to handle concave corners, simply just expanding the object and smooth out some of the concave corners, which you don't always want. So now, what does all of this framework buy us? essential. One way to think about this is, let's compare this with other planning-based grasp generators. So Obman is a data set which uses GraspIt to generate multi-finger grasps on objects. And what you notice here is almost all of the grasps in these objects sometimes feel non-realistic. They may be stable with some analytic metric, and almost always the contact is basically fingertips. So essentially we are not creating realistic grasps with smooth contacts. If there is less contact, often it's realistically less stable. And then it's also less plausible because humans don't grasp objects like this, but they are actually grasp it by wrapping their fingers around. So let's look at one of these examples with this Pepsi bottle. And this is an example where we start with a neutral pose of an optimization. We don't use any prior data or explicit adversarial losses of what the grasp should look like. This is purely optimization-based discovery of contact-rich grasps, which happen to look reasonably realistic. And the same thing actually works for other sort of objects as well. Let's say a bowl, a much more realistic grasp would basically be grabbing the bowl from the surface where the bowl rests in the palm rather than grabbing it from the sides. And the same idea surprisingly works, not only is limited to these mano hand models, but also robot hand models. In this case, we are grabbing this sort of banana model with an Allegro hand, again, using the same infrastructure of differentiable grasping. But what you notice is the robot now grabs a power grasp or aligns into a power grasp with the higher degree of surface contacts. So the big picture takeaway of differentiable simulation is use of implicit representations is a very good idea. However, we still need to figure out how this object and state representations in differentiable simulation can be used for planning downstream tasks. So just to wrap up, what I gave you is a very quick overview of how implicit representations can be used for perception, in this case, pose estimation, when the object representations are nerves. We also talked about how we can do reactive grasping, where we can use trajectory models, essentially distilled into an implicit value function. And then we talked about how we can use implicit representations of objects and scenes to enable better differentiable simulation. Overall, I think one of the key challenges and points of discussion that I'm very open to and looking forward to hearing from you guys is, in almost a lot of these places, it has been shown multiple times, some of this in our work, some of this elsewhere, where if you can get a good implicit neural function, you can get very good properties of it. However, more often than not, these implicit neural functions are overfit to the data that you're training them on. And then the data generating process is often very limited because otherwise the model won't converge. So a key challenge that remains open in this case is, how can we do pre-training and how can we use pre-trained models that we see elsewhere in deep learning or robot learning, and to achieve generalization either at object level or even at trajectory level. With that, I would like to thank the organizers for giving me the opportunity to present here, and I would be happy to take any questions. Thanks a lot for the privilege of your time.
Thank you, Animesh, for the great talk and all the demos. And thank you for sharing your insights on how to use implicit representation in perception, action, as well as in simulation. I will take the chance to ask the first question. If we want to simulate a real-world objects, we have to somehow estimate, for example, the geometry, the surface property, the friction, even, for example, the stiffness of that object. How would you propose that we should learn these kind of properties through the real-world interactions, and how are these properties should be represented in your simulation framework?
That's actually a very good question. So far we have only been focusing on, let's say, rigid objects where the properties have primarily been their texture. Particularly interesting stuff happens when you have non-homogeneous friction or non-homogeneous mass distributions, and even more interesting stuff happens when the objects themselves are deformable. I think the idea of SDF representations of objects is generic. You do not need that to be, let's say, deformable or not. People have attempted deformable nerves. However, the current ways of doing SDFs in these simulators is you pre-train these SDFs as a let's say pre-processing step, and then just use the pre-trained SDF. However, now if you have deformable objects, that adaptive SDF may not always exist, and it will slow it down if you have to train it all the way again. So I think that remains an open question, but some sort of solution such as meta SDF might be good ideas. Coming back to another part of the question, which was, what about other properties, let's say friction, masses? I think in one simple way, you could argue that neural implicit representations are essentially maps from coordinate spaces to anything in the output. More often than not, we have been using supervision in rendering. Hence, we have only output those properties, but in principle, you can output local friction as well. We will need to figure out a mechanism to supervise that. And that remains an open question. In that sense, I think the object folder work that Jiajun's group at Stanford has attempted is actually a very good direction in that space by at least studying multimodality. But of course, a lot remains to be done in that space.
Thank you so much for this great answer. Other questions from the audience? Yeah, go ahead. Wait. Otherwise, we can't hear you.
Can we just turn on captions or something? It's very hard to hear.
Ah, I see. We can do that. Yeah.
Okay, thank you. I don't.
Oh, that was okay. Any question? Yeah, Eric.
Really simple one, I think. For the SDFs that you computed between like the banana and the hand, did you decompose the geometry on the hand and then just do like individual SDFs between those objects? Or how did you compute the SDFs there? Do you know?
Yes, so the objects are separate SDFs, and the hand, I think I'll have to defer this to the actual implementation, but the hand SDF is basically treated as a kinematic linkage where each of the object has a separate SDF, or essentially it's treated as a collision.
Awesome, thanks.
Just if you're interested in something like this would be available to try in the framework called Warp. That is, I think, public right now.